Differentiability is when a function is differentiable. It is somehow connected to continuity because if a function is differentiable, it must be continuous and its derivative should also be continuous. Continuity of a function is a characteristic of a function by virtue of which the graphical form that function is a continuous wave. A differentiable function is a function whose derivative exists at each point in its domain.
Okay, graphing differentiability and continuity. If the line in the graph stop, as you can see there in the PowerPoint, it means it's not continuous. So if it's not continuous, it's not continuity. But a differentiable function must be continuous at every point of its domain. And it also means that a continuous function must be differentiable.
The theorem of this function is when a function is differentiable at a point where there is a defined derivative at a point. There are connections between continuity and differentiability. Differentiability implies when a function is differentiable at a continuous point. So therefore, if the function is not differentiable or continuous, then it is not differentiable. We can see at the example, if the function is differentiable at a point, then it must be continuous at that point. Therefore, if f of x is not continuous at x is equals to a, then f of x is not differentiable at x is equals to a.
If the function is different at a point, then it must be a continuous at that point. There are connections between continuity and differentiable. The difference implies continuity if it's a different function at, then it's different. We need to find the derivative of a function f x at a point x. Due to some reasons, I am unable to analytically compute the derivative at that point, but it can compute the derived function f(x). For all other points, we can all find out the derivative at x equals x by finding the limit of the derived function as x tends to xo.
Suppose that f is differentiable at a. This proves that the difference equation's limits exist and it is a finite real number. As indicated above, since this limit is 0, we can conclude that fx approaches fc as x approaches c, since this limit is 0 as described above.
Does not imply for the continuity if you were given an example of quantity of x equals positive x for x is greater than 0. So for the x greater than 0, the derivative is 1. Similarly, since the quantity of x equals negative x for x is less than 0, then the derivative is negative 1 for x is less than 0. A converse of a theorem is a statement formed by interchanging what is given in a theorem and what is to be proved. States a representation of an algebraic group over the others is automorphic whenever the L function of various twists of it are well behaved.
To solve this problem, the function both continuous and differentiable. At x is equals to 3, for example, in continuity where y is equal to r and f3 squared is negative is equal to a, x plus b is equal to x squared, 2 is equal to f3 square positive, and for a, 3 plus b is equal to 3 squared 2, and 3a plus b is equal
To check the continuity where x equals to 3 and 3a plus b equals to x to the power of 2 and 3, open parenthesis, 1.5
close parenthesis, plus 4.5 equals to 3 to the power 2, and 4.5 plus equals 9, and the answer is 9 equals to 9. And for the checking of differentiability, where x equals to 3.